Good evening, ladies and gentlemen. My name's Bill Wakeham, and as the Senior Vice President and most especially tonight Honorary International Secretary of the Royal Academy of Engineering, it's a great pleasure for me to welcome you here this evening for the Academy's ERA International Lecture. Just a few housekeeping items if I could first. We're not expecting a fire drill, so if the alarm sounds, it's real, and the Academy staff will make themselves known to you and direct you to the nearest exit. The other thing is we're recording this event for subsequent video playback, so I would like to encourage you all to switch off your telephones now, or at least turn them to silent. And for those of you who would like to tweet from the event, I'd be grateful if you could, in so doing, use the hashtag ERA Jackson. It'd be much appreciated. This international lecture was created following a very generous donation from the ERA Foundation with the purpose that a UK audience could hear an international perspective from an eminent person with broad engineering interests. Our speaker tonight, Dr. Shirley Ann Jackson, satisfies all of those conditions. She's most certainly eminent and most certainly has very broad interests. Indeed, in thinking out of the many activities and facets of her career that I should talk about in this brief introduction, it was quite a struggle to select one or two. Dr. Jackson has held senior leadership positions in government, in industry, research, and academia. And in all those roles, she's been a trailblazer in many senses. The first African-American woman to complete a PhD at MIT, first African-American woman elected to membership of the US National Academy of Engineering, and the first female chair of the US Nuclear Regulatory Commission. She is a member of President Obama's Council of Advisors on Science and Technology and a director of many companies, including IBM and FedEx. And she's also a former president of the American Association for the Advancement of Science. In her life as a researcher at MIT, Fermilab, CERN, and Bell Labs, she made important contributions to our understanding of novel semiconductors. And as chair of the Nuclear Regulatory Commission, she's revolutionized the treatment of risk in the nuclear industry and developed much improved reactor oversight processes. But tonight, it's her work in the field of higher education that perhaps is most interest. She was appointed as president of Rensselaer Polytechnic Institute in 1999 and has transformed the institute with an ambitious strategic effort. She has led Rensselaer to a steady rise in its rankings on the US News and World Report list of universities. In her time as president of Rensselaer, Dr. Jackson has been an influential advocate of the use of electronic media to enhance student learning. She's also promoted multidisciplinary approaches to addressing global challenges, which is an interest which fits very well with the Global Challenges Summit that this Academy will organise with the US Academy and the Chinese Academy in March of this year in London. So it's a great pleasure for me to be able to invite Dr. Jackson to the podium to deliver her lecture entitled Clouds, Crowds, Jams and Data, the New Polytechnic to Address Global Challenges. Shirley Ann, please.
Well, thank you, Sir William. And let me begin by greeting and thanking the chair and the chief executive of the ERA Foundation, the chairman, Sir Richard Brooke, and the chief executive, Dr. David Clark. I am honored to be here this evening. So let me just begin this way. Well, I'll begin by introducing my colleagues who are here. Dr. Jonathan Dordick, who is our Vice President for Research. John is a biochemical engineer, and in fact, I'll be citing a little of his work this evening. John, why don't you stand so they can see who you are? And Mr. William Walker, who is our Vice President for Strategic Communications and External Relations. Bill. He says I should call him Sir William Walker, but I told him he has not earned the title. The 2012 Summer Olympics were a triumph, especially because the event held great potential for both danger and controversy. Security guard shortages, air defenses, eligibility and doping, women and the hijab, appropriate national flag display, technology issues, and more. All of them examples of multiple intersecting vulnerabilities. Despite these challenges, this complex, multifaceted event came off smoothly, thanks to strong leadership and extensive collaboration across disciplines, professions, and the government, corporate, and nonprofit sectors. Now, the urgent global concerns that we face in the 21st century and beyond are even more complex and even more subject to intersecting vulnerabilities. These challenges, among them access to clean water, food security, energy security, environmental stewardship, health security, and disease mitigation, to delineate a few, will take all that we have in terms of ingenuity, collaboration, and good judgment. These are challenges of unprecedented magnitude, too complex to be resolved by the independent actions of those working in isolation, because they are critical to our world and, I would say, to the ultimate survival of humankind. They demand the best of our imagination and creativity, careful deliberation, tremendous resourcefulness, and the strictest focus and discipline. So how are we best to approach these global challenges? What new methods can we employ that will result in workable solutions? To meet these demands, we must engage an entirely new Polytechnic, a construct that I will explore with you this evening. Now, the term Polytechnic may sound different to your ears than to those of us across the Atlantic. The concept as I use it today is far more expansive than vocational training, and while it includes engineering, it reaches far beyond any single discipline. I define the new Polytechnic as an entirely fresh, collaborative endeavor, merging across a multiplicity of disciplines, sectors, and global regions. It is animated by new technologies and tools. High-performance computing is an example, applied in new ways with input from big data, amplified by new platforms such as the Semantic Web, probed by advanced analytics, and guided by societal concerns and ethics. Engaged in by a broad spectrum of participants, the new Polytechnic ultimately will facilitate novel and effective approaches to global challenges. The new Polytechnic enables collaboration at a deeper, more fluent level than ever before. It can help us to re-envision possibilities and clear away barriers on a vast scale. Now, although the new Polytechnic is new, it actually has rather ancient roots. Now, as you know, John Henry Cardinal Newman set us on a propitious path more than 150 years ago when he stated, "All knowledge forms one whole." In the 9 lectures that became his timeless classic, The Idea of a University, Cardinal Newman extolled the knowledge continuum to advocate for the unity of academic disciplines, but through the lens of the 7 liberal or liberating arts of the medieval university. And these were the trivium, namely grammar, logic, and rhetoric, and the quadrivium, arithmetic, geometry, music, and astronomy. Now, he used this perspective as the basis for reorganizing and delineating academic disciplines in a way that opened new venues for scholarship and for pedagogy. Now, his perspective went beyond, and this is an important point, beyond today's more limited view of the liberal arts as incorporating only the humanities, the arts, history, and social sciences, to include the natural sciences and mathematics. And he made a point of saying, and I quote, "The systematic omission of any one science from the catalog prejudices the accuracy and completeness of our knowledge altogether, and that in proportion to its importance." That is his quote. Now, Cardinal Newman understood that it was through bringing disciplines together that the new might be created, novel areas explored, and fresh solutions developed. Now, his was and is a comprehensive, even radical view at the time, and the new Polytechnic springs from his unified knowledge thesis. It will give us a surer hand in confronting and mitigating today's pressing issues. As the Royal Academy of Engineering prepares for its March summit on global grand challenges, I expect that you are cognizant that the urgent global challenges not only have intersecting vulnerabilities, but also cascading consequences and therefore unacceptable risks. So let us look for a moment at some of them. Now, from my own experience, as you've heard, I know that safety in the nuclear power arena has been enhanced greatly by probabilistic risk assessment, a detailed and systematic analysis and evaluation of interconnected systems and operations in a nuclear power station. Now, one cannot assess risk in a nuclear station merely on a component-by-component basis, nor by having experts examine individual systems in isolation from one another, without knowledge of their interactions or without understanding how people interface with technology. There is a connectedness of the systems in nuclear power stations and connectedness of the people with the systems, which in fact can lead to cascading effects in the case of a triggering event. As we have learned over the years, the correct estimation of the magnitude and likelihood of a disaster and how to mitigate it can be made only when the perspective and knowledge of experts from a variety of disciplines and sectors are brought together. If not, there can be cascading consequences. We regularly get reminders of what can happen. Superstorm Sandy in the United States recently, the Tohoku earthquake and tsunami in Japan, and the extreme heat waves in Europe in 2000 and 2003 and 2010, in fact, are examples. The earthquake-induced tsunami resulted in extensive damage to the nuclear power reactors at the Fukushima Daiichi site, wrecked infrastructure and homes, contaminated the environment, threatened human health and food safety, disrupted manufacturing and supply chains, shifted capital, and as a consequence, had extensive economic impact, certainly in Japan and across the world. Superstorm Sandy devastated extensive areas of the New York and New Jersey coastline. My husband and I have a home in New Jersey. We experienced some of that. And of course, it flooded most of lower Manhattan. And this has prompted far-reaching discussion of how and whether to rebuild private homes and to protect public infrastructure against future storms, and of course, how to pay for it. The two European heat waves, unlike any experienced in the previous 500 years, were blamed for thousands of deaths and led to health crises, fires, and drought, which created crop shortfalls and negatively impacted national gross domestic product. Now, a true new Polytechnic approach can help us to assess, evaluate, understand, and mitigate the effects of any future occurrences, and to address, then, the grand challenges of this century. We have seen bursts of inspired inter- and multidisciplinary integration before. In fact, an example hails from the 19th century at the university where I serve as president, Rensselaer Polytechnic Institute. Now, the institute did not at its outset include Polytechnic in its name. This designation came only after one of its senior professors and later director of Rensselaer, Benjamin Franklin Green, toured Europe and saw the advantage of an education that incorporated multiple disciplines. In particular, he saw the value of deepening engineering students' understanding of the sciences so that they could do more than just faithfully reproduce or merely extend prior art. He proposed a new curriculum, putting scientific thinking at the core, and added Polytechnic to the Rensselaer name. He wanted students to study science, literature, philosophy, rhetoric, and the arts as a foundation for developing more technical knowledge and skills. This undergirds our curriculum today. With these changes, students could use emerging knowledge of the sciences, mathematics, and the arts to innovate in engineering. The design and construction of the Brooklyn Bridge in New York City is a wonderful example of the thinking engendered by this kind of education. The work was guided by Rensselaer alumnus and chief engineer of the project, Washington A. Roebling, and his wife, Emily Warren Roebling. In his inspired work, engineering and the sciences came together to innovate better bridge support structures, pneumatic caissons, and wire cables spun in situ. Now, in fact, he gave up his health to effect this design. The bridge also is appreciated for its beauty, which was aligned with its engineering design. Now, you may be familiar with the diaspora of scientists, many of them physicists, at the close of the Manhattan Project, the great research program involving the United States, the United Kingdom, and Canada, which, as you know, produced the first atomic bomb during World War II. At the close of the project, some of these talented and skilled researchers and academics brought their tools and rigor to new research, where they did foundational work in the life sciences and biochemistry. Now, I will highlight two who in fact crossed scientific disciplinary boundaries. When he joined the Manhattan Project, English physicist Maurice Wilkins had been working on spectrographic separation of uranium isotopes for use in bombs. His later research contributed to the scientific understanding of the structure of DNA. And with Francis Crick and James Watson, he won the 1962 Nobel Prize in Physiology or Medicine. Martin Kamen, a Canadian-born American physicist and chemist with the Manhattan Project, helped to discover carbon-14 and is credited with discoveries in biochemistry leading to the understanding of plant photosynthesis and metabolism. He won the Enrico Fermi Award in 1996. Now, Cardinal Newman would not have been surprised by this. But let me amplify this further with examples from a few current and important realms of endeavor: biotechnology, infrastructure, and social cognitive networks. In the US, certainly, if not globally, medicine and biomedical research are at the center of a storm of economic and social concerns. We already are seeing how genomics, artificial organs, embedded sensors, and expert systems are transforming medical care and treatment. Emerging interdisciplinary research and startling new discoveries are bringing disruptive change and hope. In October of 2004, in Afghanistan, a mortar exploded, and a U.S. Marine Corporal, Isaias Hernandez, was nearly ripped apart by shrapnel, which tore away 70% of the muscle in his right thigh. You see him in this picture, and fractured his femur. Corporal Hernandez endured 4 years of surgeries and physical therapy to little effect until he met Dr. Stephen Badylak of the McGowan Institute of Regenerative Medicine at the University of Pittsburgh in the U.S., who cut open, once again, the corporal's thigh and applied a new gel-based therapy, an extracellular matrix derived from pig bladders. Now, as you may know, the extracellular matrix fills the space around the body's cells. It contains hormones, structural proteins, and other molecules that maintain cell function and health, mediate intercellular communication, and importantly, guide tissue growth. After about 6 weeks, the implanted gel mixture spurred the growth of muscle tissue, tendons, and vasculature, and with it, restored physical strength to the Marine's thigh. Now, Dr. Badylak does not entirely understand how the extracellular matrix works, but what is known is this: it becomes part of the existing tissue. It draws stem cells to the implant location. It shifts the body's immune response from rejection to reconstruction. By recruiting the body's own stem cells and putting them to work, the extracellular matrix obviates the need for controversial and difficult stem cell implants. Think of it as a kind of biological catalyst. The work I've described is part of a U.S. government-supported regenerative medicine research program at the University of Pittsburgh. The work draws upon a multiplicity of disciplines, including biomedical engineering, nanotechnology, tissue engineering, drug discovery, and health informatics. Rensselaer faculty in our Center for Biotechnology and Interdisciplinary Studies are engaged in similar multidisciplinary research, deriving breakthroughs in the use of adult stem cells, understanding the role of the extracellular matrix in cell signaling and tissue regeneration, developing, and this is Dr. Dordick's work, developing enzyme-based coatings that kill methicillin-resistant Staphylococcus aureus on contact. Bioengineering synthetic heparin, and understanding how to mitigate the role of both H and N proteins in flu virus transmission. Modeling the role of hemodynamics, essentially blood fluid dynamics, in heart disease, and developing powerful new approaches to medical imaging from multiple sources, and much more. Now, these breakthroughs all come from research at the intersection of the life sciences with engineering, the physical, and computational sciences, what one might call a medical Polytechnic approach. The work of Robert S. Langer, an engineer and institute professor at MIT, my alma mater, is a consummate example. His activities are anchored in biomedical engineering, but by reaching into areas such as nanotechnology, tissue regeneration, drug delivery, and even business, and collaborating across sectors, he has created innovations that have been awarded more than 800 patents, built the largest biomedical engineering laboratory in the world, founded or co-founded more than 24 companies, and provided hope and better health for patients worldwide. Dr. Langer is a recipient of both the U.S. National Medal of Technology and the U.S. National Medal of Science. He also is a member of the U.S. National Academy of Engineering, the U.S. National Academy of Sciences, and the Institute of Medicine. In fact, he is the most cited engineer in history. Nor does interdisciplinarity stop with the examples cited. Today's medical school graduates may be the first generation of doctors to include an entity with artificial intelligence on their teams. Watson, the computer that beat out the best human contestants on the American television quiz show Jeopardy, was designed by Rensselaer graduate Dr. David Ferrucci and his colleagues at IBM. The social, cognitive, and computer sciences, as well as engineering, came together to create Watson. Now IBM is adding medical science to the mix. They have sent Watson to medical school at the Cleveland Clinic to absorb all existing medical knowledge that the Cleveland Clinic possesses, and to use that knowledge to derive data-driven answers to numerous medical questions. Now, this takes health informatics to a new level of sophistication. All of these developments in biomedicine and more will help us to address global disease mitigation and health security in entirely novel ways. Another example of the new Polytechnic is aimed at the development of sustainable built environments and civil infrastructure. Buildings account for more than a third of the total energy consumption in the U.S. and nearly 40% of its carbon dioxide production. Now, as construction increases exponentially in emerging economies, it is especially urgent to accelerate the pace of architectural innovation through the use of sustainable materials and cost-effective, energy-efficient technologies. At Rensselaer, the Center for Architecture, Science, and Ecology, or CASE, is developing new approaches to addressing this need with radically new next-generation building systems. Now, CASE, in fact, is a multi-institutional and professional research collaboration between the university, other entities, and the globally focused architecture firm Skidmore, Owings, and Merrill. CASE is pushing the boundaries of environmental performance in urban building systems using actual building projects as research testbeds. Natural systems and emerging technologies are brought together with stunning design to create structures that include integrated and distributed on-site energy harvesting, transformation, storage, and redistribution. It includes biomechanical air filtration and dynamic daylighting systems. Researchers at CASE are developing a building integrated photovoltaic system, which takes a dramatically different approach to providing interior space with electrical power, thermal energy, enhanced daylighting, and reduced solar gain. It surpasses existing building integrated photovoltaic or concentrating photovoltaic technologies and is applicable to both retrofits and to new construction. The system integrates into facades and atria, harvesting solar energy while still providing outside views and diffuse daylight. It accomplishes this by miniaturizing and distributing the essential components of concentrating photovoltaic technology within weather-sealed windows. Electricity is produced by an array of photovoltaic cells, Much of the remaining solar energy is captured as usable heat, reducing interior solar gain loads, and that means loads on HVAC systems, while daylighting reduces the need for artificial lighting. Research at CASE combines materials science and engineering, architectural design, and the aggregation and analysis of data from embedded sensors to provide feedback for optimal building performance. The work is complex. Developing even one dynamic solar facade to maximize solar energy use requires the input of as many as 30 individual disciplines, including physics, optical engineering, mechanical engineering, and lighting. The research results in new performance-driven building technologies that create clean, self-sustaining built environments and help to meet environmental stewardship and energy security needs, all within a novel architectural framework. And what these examples progressively illustrate is the importance, the increasing importance of data-driven innovation. The explosive volume, timeliness, range, and fungibility of data are unprecedented and contain an inherent interconnection, which has the potential for creating novel approaches to collaboration. Today, we also have unprecedented capabilities in data access, aggregation, and analysis, married with high-performance computation. The internet is the new library, with more information than any one individual can ingest. Social networking leaves behind digital crumbs for us to follow and study. Sensors and networks are embedded in everything, from buildings to automobiles, of course, to cameras, to satellites, and are creating what often is referred to as the Internet of Things. All of this produces trillions of bits of unstructured data, often in differing formats. The resultant collection of massive data sets known as big data is more accessible today and shared more widely than ever before. The ability to process that data in an efficient and relatively inexpensive way provides us with new bases for decision making. It also brings data to more participants and allows them to manipulate it, to discover patterns heretofore invisible. The U.S. federal government has opened many of its databases through a website called data.gov, which provides public access to high-value machine-readable data sets. And yet, one could say, as one of our faculty likes to say, that concerning big data, we are still pre-web. Now, the World Wide Web is one huge library, but it has not yet provided uniform access to data. In a word, there is no Google for all data. Data comes in multiple forms: words, numbers, images. Moreover, although it is becoming a new natural resource, data today does not express relationships. Data discoverability has been difficult, since one needs a consistent way to refer to data. A data object identifier, something like an RFID tag, that will endure as data is entered into a registry. Data tagging would identify its origins, history, context, rights, and much more. Even tags on database entries that identify whether numbers, once abstracted, are metric or English, often are lacking. So we need a better means to take what may be implicit in the data and obvious in context and make that explicit in its description. We also need to improve the credibility of information by automating processes that cross-reference and cross-check. One remedy, the Semantic Web, is a collaborative movement really started by Sir Tim Berners-Lee and led by the World Wide Web Consortium, which includes a number of Rensselaer professors, to promote common data formats on the World Wide Web. More broadly, the Semantic Web itself has been described as a mesh of information linked in such a way as to be easily processable by computers themselves on a global scale. The approach is based on the same technology that Watson was based on. It is based on semantic technology that encodes meanings separately from data in content files and separately from the application software. And in fact, new web-based architectures and ontologies based on semantic technology allow intelligent software agents to search for connections among different data by semantic inference. One can only imagine what the impact will be once this work is completed. Now, digital connectivity, beyond the production of data in and of itself, is leading to a whole new thrust that marries data, technology, and the social and cognitive sciences. The torrent of digital footprints from social networking is giving us a new ability to predict human interactions in a verifiable way. Now, researchers at the U.S. Army-sponsored Social Cognitive Networks Academic Research Center at Rensselaer are in fact studying fundamental social cognitive network structures and how they are mapped onto and altered by technology. The research strives to measure and model the interactions that people engage in over these networks, and in the process, to uncover and to foresee complex social patterns, and to understand how technology enhances or changes those patterns. In particular, the center studies dynamic processes, the flow of knowledge, the workings of constituent networks, which could include adversary networks, levels of trust, with particular attention to cultural nuance, and the impact of human error in social cognitive networks. The research can help us to understand social movements beyond the kind of simplified way we think we understand them today. It can help us understand or even predict the spread of corruption or potential threat. But you know, the very ubiquitousness of the internet and its overall connectivity create vulnerabilities. The internet was designed to provide broad access, which exposes it and other linked networks to security threats, such as malicious software, which can invade privacy and damage business systems and even control systems for critical infrastructure. Since the overall architecture of the World Wide Web and the scale on which it exists is difficult to change, there is a nascent discussion of novel approaches to software development in order to detect and protect against malware. One idea is to replicate a living organism's immune response to an invasive species. Now, all of these approaches suggest that a highlight of the new Polytechnic is that it can link the capabilities of advanced information technology, communications, and networking to other fields, such as the life sciences, the physical, social, cognitive, and computational sciences, all at once. Now, the success, however, of the new Polytechnic demands first that people understand and find ways to use the capabilities inherent in big data and hyperconnectivity. And second, that people better appreciate how social and cognitive demands influence the success of endeavors that use these capabilities. The ability to aggregate, integrate, validate, structure, and fully use the burgeoning mass of information available portends a data-driven future under a rubric that I refer to as clouds, crowds, jams, and data. Now, I've provided some detail on data, in particular big data. Now, I will describe the rest. Cloud computing, as you know, delivers data, software, and computing capability over a network. It could be the internet or a proprietary network on platforms shared by multiple users. In a sense, it is a virtual time-sharing environment. The cloud brings information and processing power to the mobile world, making it practical for individuals in the field or executives on the move to access and to share vast amounts of information. It supports advanced visualization systems in which matrices of data from a variety of sources are put together in ways that allow them to be understood despite their complexity. Crowdsourcing allows us to engage the expertise, perspectives, and enthusiasm of many people, including those who previously may not have had a voice in issues that may concern them. The process involves outsourcing a question, a problem, or a task to a dispersed group, sometimes a very geographically dispersed group of people, most of them unknown to each other. The good news is that crowds can help to identify problems even, suggest ideas, and assist in the execution of solutions. Wikipedia provides a good illustration of the pluses and minuses of crowdsourcing. While Wikipedia is a rich resource and a powerful starting point for research, crowdsourcing means that a particular topic or entry in Wikipedia may be riddled with errors. In fact, it once gave me a sister I did not know I had. I checked. I never had the sister. So it may be riddled with errors, despite the efforts of many who make corrections to it. Now, some of the errors may be ephemeral, others persistent. Some are added in good faith, meaning they weren't added as errors, others maliciously. And this raises concern of trust and validation in an online world, a theme to which I will return. Perhaps less familiar is the idea of the jam, which also brings together dispersed but often organizationally linked participants to concentrate on a selected challenge over a short period of time. You can think of it as crowdsourcing, where the participants typically have a shared background or more formal connection. Working from shared data sets, propositions, and questions within a carefully designed framework, experts and interested parties in a jam use online collaborative tools to share knowledge, express concerns, and brainstorm issues and their solutions. Although the approach embedded in the concept of clouds, crowds, jams, and data marries high-performance computing, even immersive environments, augmented reality, social cognitive networks, online collaborative tools, semantic web platforms, and intelligent agents, all of this, as massive as it is not the full substance of the new Polytechnic. Why? The new Polytechnic unites the cognitive and social sciences, the physical and computational sciences, the life sciences, psychology, sociology, the arts, history, language, linguistics, engineering, and more. As a construct rooted in what Cardinal Newman envisioned, that all knowledge forms one whole, it offers a powerful new tool for approaching pressing global challenges. This reaches beyond traditional research. It is leading edge, and its impact on the future will be far-reaching. But beyond theory and application, and the integration of tools and technology and disciplines, how will the new Polytechnic affect leadership? It is early yet for real scholarship on that subject, but there are some things we can surmise. New technologies always alter leadership. Leaders generally possess charisma of some kind. You know, that elusive magnetism that attracts supporters and enables a leader to influence others. Research traces the advent of the idea of charisma directly to technology. Until sound could be amplified, leaders required thunderous speaking voices, something actually that you notice when listening to early recordings of public speaking. People always seem to be shouting. The coming of radio marked a clear shift. People could speak more naturally, but had to be interesting, or listeners could change stations. Now, with television, it became critical for leaders to exude the kind of personal charisma that we look for and sometimes recognize in leaders today. Of course, the timeless leadership characteristics remain. Clear vision, well-articulated mission, goals, strategies. Leaders still must inspire and motivate, offer support, be intellectually stimulating. They still must be exceptional listeners and questioners and possess emotional intelligence. They must mine for trends, sense opportunities, judge risks, and of course, communicate. Effective use of advanced technological collaborative platforms strongly suggests a shift that incorporates but goes beyond traditional leadership, both in process and in personal approach. The new Polytechnic requires that leaders acquire new skills for a digitally interconnected environment, that they balance authority with engagement, understand nuances of culture and language, and seek ways to establish trust among, within, and between virtual teams. With more diverse, digitally connected audiences, participants who may never before have had a voice and may even be volunteers in an enterprise, and with less hierarchical dynamics, there will be concern about trust on multiple levels. So leaders must recognize the value, even more than before, in divergent perspectives and manage opposing expectations. And they must accomplish all of this in a virtual environment where the leader may never look participants in the eye or shake their hands. To bring people together, leaders in this new context must have the ability to translate between and among disciplines and sectors, between the digital and the human. They will need to incorporate analyses and insights from diverse fields, including the cognitive and social sciences, and to bring this ability to bear on any given challenge. Now, I will add ethics to this list. In the face of unintended consequences and uneven impacts, leaders will need to be even more acutely sensitive to the implications of decisions. Leadership through social cognitive networks brings a greater need to balance security and profit with concerns of privacy and reputation. Consider the many perspectives that must be accounted for in the use of nuclear energy or genetically modified crops. A fundamental question always will be, and this creates the knife edge, a fundamental question always will be not merely can it be done, but should it be done? Models are difficult to come by because the new Polytechnic is, after all, new. On the one hand, capable leadership in any era rests on identifiable characteristics and makes use of the technologies available at the time. Now, so to close, let me reference a leader who, though he did not have access to the technologies of which we speak today, nevertheless offers a compelling model of character and abilities that apply to the new Polytechnic. He profoundly united diverse groups from vastly divergent cultures, languages, environments, expectations, and viewpoints. He found solutions to urgent vulnerabilities. Now, you may know this story, and I'm sure you do, but it is worth retelling in the context of the new Polytechnic. As the first democratically elected president of South Africa in the new post-apartheid era, Nelson Mandela sought to unite a nation riven by bitter and deadly racial animosity. During the 27 years he spent in prison for militant anti-apartheid activities, he learned the language, culture, beliefs, and values of the fiercest apartheid proponents, his Afrikaner prison guards. And that understanding, plus his personal optimism, dignity, diplomacy, sense of fairness, intelligence, and grace, gave him profoundly effective tools. Seeking national reconciliation early in his presidency, Nelson Mandela chose the unifying power of sport. In 1995, South Africa, as you know, hosted the Rugby World Cup, the first major sporting event held there following the end of apartheid, and the first in which the Springboks were allowed to play. Now, that team long had been the embodiment of white supremacy and oppression. The blacks detested the game. They detested the primarily white team and the green Springbok shirt. In fact, they routinely cheered the team's opponents. President Mandela carefully wooed leaders on all sides, persuading them to a role in unifying the nation, recruiting them to a new team slogan, "One team, one country," and the notion that the box belonged to all of us now. Springbok players learned to sing the old song of black resistance, Nkosi Sikelele iAfrika, God Bless Africa, which had become the new national anthem. They sang it at the beginning of each tournament game. Although pundits predicted a loss for South Africa in the Rugby Cup, the Boks posted a string of playoff wins. South Africans of every color and political stripe increasingly became enamored with the team. On the morning of the final game, President Mandela, wearing a green Springbok jersey and ball cap, stepped onto the pitch to shake hands with the team. After a stunned silence, the crowd at Johannesburg's Ellis Park Stadium erupted in thunderous cheers. To top it off, the Springboks won the game in overtime, sending the nation into joyous delirium. So what is President Mandela's enduring message for us? Don't address their brains, address their hearts. Well, it is impossible to characterize Nelson Mandela without superlatives. But for our purposes this evening, his role in this, rooted in profound understanding of and empathy for all parties, with a 30,000-foot vision of national unity, with authority, political engagement, personal charisma, and a willingness to risk, distills the essence of leadership genius. Now, I certainly do not suggest that new Polytechnic leaders all will be involved in situations as perilous as those faced by Nelson Mandela. But his personal vision and characteristics should stand as important models and metrics for addressing the most urgent challenges of the 21st century. President Mandela led a kind of new Polytechnic of his own, using the technologies and means available at the time. Imagine what miracles he might have achieved had he had access to the tools of today. So as we have seen, the new Polytechnic is an intellectual construct, a new way of thinking, a new way of doing. It will impact research in powerful new ways. It will impact pedagogy as we enlist the next generations of students in this construct and educate them to be leaders in the digital economy. The new Polytechnic will more fully utilize data in ever more sophisticated ways while exploiting our ubiquitous interconnectivity. In fact, the interconnectivity of people and things is generating massive amounts of data, as I've said. But to make sense of all of that data requires us to exploit the very interconnectivity to collaborate in new ways. It requires us to break out of disciplinary silos, exploit new technological tools, employ high-performance computing, data analytics, data aggregation, and ultimately to embrace Cardinal Newman's concept of the knowledge whole, to address access to clean water, to food and energy security, health security and disease mitigation, and other urgent global challenges. The new Polytechnic, utilizing advanced technology to amalgamate a multiplicity of disciplines and perspectives, can lead to greater vision and deeper understanding. And it is our best bet for assuaging the human hunger to know, to remedy, and the human desire for uplifted lives. Thank you very much for your attention.
Well, Dr. Jackson, thank you so much for that enthralling journey through many different dimensions, I think, and your interconnectedness, I think, is a very strong theme. It's now the chance for the audience to ask a few questions. Could I ask, please, if you do have a question, to indicate to me, and I will point to you. Then there is a microphone which we'd like you to use, and please, if you could identify yourself and your affiliation, be most helpful, given that we're recording the session. So can I begin by asking for some questions, please? Yes, please. Right in the front here.
Hello, my name is Martin Durrani, editor of Physics World. Thank you very much for a very interesting talk this evening. And one question I have for you. You mentioned the contribution of Benjamin Franklin,
Benjamin Franklin.
I apologize. Who back then suggested the importance of multidisciplinary work. Given that, why do you think it's so difficult to bring people together? Do people like to live in their silos? Is that a real problem in trying to create the vision that you portrayed?
I think people like to live where they are comfortable. It's interesting. I'm sure you may be familiar with the columnist Tom Friedman, and he wrote a book, The World is Flat, and he talked about globalization and so on. Before he wrote that book, he wrote another book called The Lexus and the Olive Tree. And the idea of the Lexus at that point was an example of a kind of globalization because of the penetration of, that vehicle globally, the penetration of technology globally. But the olive tree referred to the need people have to have a rootedness. And so I think those two kinds of forces play off against each other all the time. And so then when one translates that into a scholarly domain, and people spend many years learning and becoming ever more steeped in a discipline, I do think some of this is reinforced in fact, by how we educate people, but they become steeped in a discipline. And that becomes the pathway for success for them, then it is difficult. On the other hand, scientists themselves and engineers have always collaborated. And research has always been a global enterprise. Now, typically more within disciplines in the earlier days. But the connectivity of which I spoke both offers new opportunities and is driving new behaviors.
Thanks for that. Yes, please, just here.
Russell Harmon, U.S. Army Corps of Engineers. I want to just return to your point with education. The vision you discussed for the Polytechnic requires a whole new educational paradigm. How do you see that, and what is Rensselaer doing to realize this new paradigm?
Thank you.
Now, that's a good question, and let me talk about it along a couple of dimensions. We still educate students in majors. They do mechanical engineering or physics or something in the life sciences. But we very deliberately work to have them engaged, even as undergraduates, in research and to work in teams. And then what we are doing is, in fact, developing relationships to send them abroad and to send them, in fact, in teams abroad as much as possible to work on challenging questions that could be in research or it could be on a design project, but especially in emerging economies where they don't always have all of the tools at their disposal. And part of the reason I used Nelson Mandela as an example, aside from the fact that I have always found him to be very inspirational, is because Rensselaer, interestingly enough, has a relationship with Stellenbosch University in South Africa, which is interesting because, as you know, Stellenbosch was in fact the intellectual home of many of the Afrikaner leaders. It now has a black rector or head of the university. Both institutions, Rensselaer and Stellenbosch, have a Dutch root. And so we actually, in fact, use that connection to team up groups of our students with students at Stellenbosch to work on problems and then to have exchanges where our students will go there and their students will come to us to culminate what they do. So that's one example. A second is that we have very deliberately, under our university plan, created a new kind of interactivity with what some people refer to as the flipped classroom, where students do online learning even before they come to class. And they also do culminating projects with teams in industry as seniors. This is for the engineering students. And then, because we actually have our own supercomputer, because we have one of the gentlemen who was a developer of the Semantic Web, and because we have people who are strong in data science, we're beginning to do all of these things that I talked about, and to actually apply them to solve important problems. We built a Center for Biotechnology and Interdisciplinary Studies that is designed architecturally as well as intellectually to work on problems at the intersection of the life sciences with engineering, the physical and computational sciences. I gave you some examples of some of that work. But the actual design of the facility is not one professor, one lab. It has open bay laboratories that have multiple groups working in them. In fact, Professor Dordick was, and still is briefly, the director of the Biotechnology Center, but he recently was promoted to be our vice president for research.
Yes, gentleman with the shirt there, please.
Martin, Professor of Computer Science at Greenwich and Council of Professional Science and Computing. Given what you talked about the olive tree and the development of the new Polytechnic, I'm interested to know your view about the relationship in the future for the new Polytechnic between the physical and the virtual, particularly in terms of the learning spaces.
Thank you for asking that question. And I'll go back to the question the gentleman here asked. We actually have at Rensselaer what is known as the Experimental Media and Performing Arts Center, or impact. And what it is both an artistic platform for the time-based performing arts and a research platform. And the same spaces are designed to accommodate both. And in fact, each of the spaces is capable of supporting immersive virtual reality, augmented reality spaces. And as well, we have a technology park, a 1,250-acre technology park, which is home to our supercomputer center, but also has an emergent reality lab in it, which is kind of the sort of the beginning end of creating that. But the impact spaces actually allow us to create virtual environments at human scale and to use them for everything from architectural design to creating realistic scenarios so that people are inside the data, to creating new learning paradigms for the study of languages, and to use even gaming to create the interactivity, but in human scale and beyond spaces, to bring the digital and the physical together. And so, in fact, we talk about it as where digital meets reality and going beyond the traditional classroom. And so, in fact, we're doing that, and we would be happy to talk with you about it afterwards.
Thanks very much. The gentleman behind, please.
I'm a civil structural engineer. Thinking about the beneficiaries of the vision you paint, potentially it could be society as a whole, which demands altruism on the part of people who hold the data. On the other hand, it could be major corporations, companies. They will want to preserve the commercial secrecy to enhance their own wealth creation for themselves. How do you square the two?
Well, you know, it's interesting because there's this whole set of questions that people raise about who owns the data. And if one gives up the data, does one own it anymore anyway? Typically, the monetization of things like this comes about through the use of the data, you know, what is done with it. And certainly there will be commercial interests that, in fact, will want to make more proprietary uses of data. But some of the data exists and will be in a kind of public commons. In fact, the US government, through this data.gov, is putting pretty massive data sets on the web for people to be able to use, to combine, and inviting people to write applications based on that data. So I think there always is in society, with the development and evolution of any technology, this kind of interplay and even tension between private use and public use. But let me give you an example of something that is a public use that I think more people are motivated to do than you might expect. You know about Hurricane Katrina that occurred some years back in New Orleans and the whole Gulf Coast, where the levees failed. In fact, some of our faculty, led by one in particular, worked with the U.S. Army Corps of Engineers to, in fact, model the levees and why they failed, and then to help with the design of better levees. But a key part of being able to adapt to climate effects, to weather effects, is to be able to monitor, and monitor in real time, in this case through distributed sensor networks, what is happening with both the weather, other climate-driven effects, and the infrastructure, and to bring those data sets together. And that's actually happening as we speak. And those things are then being used both to monitor what happens with existing infrastructure and to have that go forward to help with designing better infrastructure. So, but there's always that interplay.
One last question, please. Yes, gentleman in the middle.
I'm Antonio Tarrisi, I'm from Imperial College. And I would like to ask you, in your opinion, how the new Polytechnic would represent an occasion in tackling global challenge, which need sometimes different local solutions. So actually, it's not only a discourse about multidisciplinarity, but also multiculturality and understanding what is the new Polytechnic approach to this problem.
Well, I think it has impact in two ways. The new Polytechnic does not preclude those who are in a given geography, a given region, from applying approaches like this in a collaborative way to solve important challenges. But here's the thing. The real beauty of, let us say, crowdsourcing is that a question that can be posed that's relevant to you, where you live, but you get to amass 1 million minds to posit solutions. But then you get to decide how relevant those solutions are to you, or as a participant in the collaboration, to shape the direction that the inquiry can go. And so again, I always say that technology is as technology does, but technology does not do alone. People use technology. And so we're only limited by our good intentions, our own intellects, and our own desires to use technology in ways that can uplift people. And that's why I'm in the business of educating scientists and engineers, but have them exposed to the limits of technology, how technology can be used in environments that are different than the ones they grew up in, and how that the use of that has to be relevant for other people in other contexts. But I think it's exciting.
Thank you very much.
Thank you.
And thank you all for many interesting, stimulating questions. I think the nature of those questions reveals the profound nature of what Dr. Jackson has spoken about so clearly. Her own connectedness, I think it should be obvious to you all, that she has, in her career, spanned many disciplines and activities and is now thinking more profoundly about how that can influence others. She's caused me to think tonight myself about leadership in this world she describes, and it does seem to me a rather different place than leadership has been. But whatever, I'm grateful to you, very grateful on behalf of the Academy for delivering such an excellent lecture that's been so stimulating. So can I thank you and ask you to thank Dr. Jackson with me.